neuromation is involved in many different sectors within the AI industry. We're in the retail automation with our partners OSA, where we are helping them use image recognition to understand different products on the shelves throughout Europe. As you can see, we've already cataloged 170,000 items, which we are creating a very huge data set in order to do so. We're also involved in the pharma and biomedical tech, where we are helping companies classify and understand medical imagery a lot better, so that's saving time for doctors in terms of classifying tumors, melanomas, different types of cancers, strokes, and anything else that you can think of by using medical imagery. Apart from that, we're using smart cameras to watch patients and babies and elderly people, so that we can always understand what's going on from a higher level. Apart from that, we've also got enterprise automation, where we are helping train flying drones and autonomous cars and different types of manufacturing companies and supply chains, so that everything is automated and we're leaving no room for human error. So how did neuromation basically come about? We noticed that there was a bottleneck in AI, that in order to create a very efficient model or machine that can think for itself, you need to have immense amounts of data. And we noticed that there's not enough labeled data out there. And apart from that, there's not enough data that small and medium enterprises have. So what we did is we thought up a way to create synthetic data. And basically what this means is we create virtual 3D images of whatever we're looking to recognize or whatever task we're looking for the model to do. So if I take into consideration a normal company looking to create a data set, they're gonna need at least 1 billion labeled photos. And what does that mean? It means that you have to take 1 billion photos and you have to send it to a data labeling service where they will sit and tag each photo and each element within the photo. And on average, one person, 8 hours a day, can do about 50 images for about 0.2 cents per image. At the end of the day, it's years of mechanical work, and it can come up to 240 million. And that's before you've even got started. So as you can see, it's a lot of money that you need to create very efficient AI. So what have we done and how to solve that? So as you can see, these images look beautiful, they look amazing, but they're not real. This is synthetic images, synthetic data that we have created especially for the retail sector. So what we did is basically we took the products themselves, created and rendered a 3D image which comes out pixel perfect and already labeled. The computer can understand exactly what's in this image without us telling it what to do. Once we have this 3D image, we can then take it and multiply it and put many of them on a shelf. We can take it and we can put it on the moon. We can put it wherever we want in order to recognize it and make sure that we are understanding exactly what the camera is seeing. And how is this basically helping? So first of all, synthetic data comes out 100% accurate in terms of labeling. There's no mistake because there's no human error. It's a lot automated, so we can generate as many photos as we want depending on what we're looking to do. It's a lot cheaper, it's a lot faster, and there's no manual labor involved. Apart from that, the three main things that you need to look at in terms of data labeling is accuracy, automation, and speed. Once you have all of those three elements, you have what you need in order to create a perfect data set to train your models to understand exactly what you needed to do. So I want to talk a little bit about the use cases of neuromation and what we're doing and how we are doing this. So for instance, this is in the healthcare. It's a partner of ours called Mom Baby, where we're using computer vision to look at babies and understand what is going on with them while they sleep. Now, it might seem like a very simple concept, but I don't know of anyone who's gone and taken lots of photos and images and films of sleeping babies. It would be a bit weird, don't you think? Filming sleeping babies. So basically what they did is they started off with a little sensor. which you put on the baby, and the sensor can check the heart rate, the breathing, the temperature, and a little bit of the movement. Okay, but that's not enough. What happens if the baby is sleeping with his hands over its mouth? What happens if the baby's nose is blocked? What happens if there's something that's fallen on the baby or obstructed or around the baby that the sensor cannot pick up? So we've created a camera which watches the baby from above in connection with the sensor in order to create a whole solution. And this will alert the parents at any time when something is wrong. But how did we do that? So basically we created synthetic images of babies and created synthetic sleeping babies so that we could create an image for which we can train the models to learn what a sleeping baby is and how it's moving and how to pay attention to certain things inside. So another use case that we're also doing, which is a little far-fetched in terms of conceptual understanding with in silico medicine. Basically what we're doing, we're using neural networks and AI and synthetic data to create virtual worlds where we can create experiments. Today, if you want to create a new drug, you have to have scientists, you have to have a laboratory, and you have to have all of the different molecules and proteins and everything else that you need to run the experiment. Once you start running the experiment, you start understanding what's going on. But that can take years, it can take time, and it can take money. So what we said is, why don't we do these experiments with AI in a virtual world? So we're helping them save time and money by running the experiments ahead of time, understanding what the results they got via the synthetic data and via the virtual experiment. And then if they got the results that they wanted, they will then go and try that experiment in real life. And then they will really see the results. So it's helping save a lot of time and a lot of money. Basically how we're doing this is with computer vision for 3D molecular structures. We as human beings, we understand what an oxygen channel looks like, or a carbon channel, or different types of molecules. We already know what they look like in terms of its 3D image. So what we did is we created synthetic images of these different molecules, okay, and we placed the elements and parameters and exactly what those elements do when they interact with each other, and we allow them to interact with each other in a virtual world so that scientists can do experiments without actually having to use these molecules. Once he understands what the results are and what happened at the end, and if it's what he wanted, then they can go into the real trial and actually try the experiments for themselves to get real results. But this is just a beginning stage to help them understand the direction and put them and help them focus exactly where they need to go in terms of their experiments and data collection and drug discovery. Another thing that we're also doing with another client of ours, with the European Molecular Biology Lab, is machine learning for medical imagery, as I explained before. These are MRI scans. Okay, now today you go to a doctor, you do an MRI scan and the results come out and they send it to another doctor and he analyzes it and he can ask another doctor for a consultant to look in and so forth and so forth and so forth. It can take a long time, and at the end of the day we're basing ourselves on human intuition and on what this professor has learned throughout his experience and throughout his career. But a lot of the times, and around 20% of these times, there is wrong diagnoses. And 20% is a lot in the medical world, because even 0.001% can kill somebody. So can you imagine what 20% can do? So what we're doing with this is, first of all, we're helping them create deep learning models to understand what is happening in this image. And it's not going to tell the doctor yes or no. It's going to tell the doctor, hey, look here and look here. And it's going to help the doctor focus so that he can get a more educated answer and get to the point, or to the solution, and understanding what's happening exactly within this MRI. And we're also doing this by creating synthetic data as well. We can basically create a synthetic brain, which is a perfect brain. A pixel perfect brain, and we can teach the model to understand this is a perfect brain, and then every time he sees something different, he will then flag that and say to the doctor, hey, this is not what I'm used to seeing. Take a look at this, please. And that way doctors can focus in terms of time and understanding and looking at the images. A lot of the time we go to these doctors and they're very busy and they've got millions of patients and a lot of time, and we never know if we're getting the treatment that we need. But this way we know that the doctor will look at what he needs to look at. And even if he's happy, and even if he's sad, or even if he's depressed, or even if he had a fight with his wife, we will still get the same answer because we will direct him to look at what he needs to look at. So basically, how does this work? I mean, the whole deep learning for medical imagery. Basically, it started out in 2016 in terms of understanding and how we want to do it and how we want to process it. And we've got to the world of 2017 where we could actually scan these images and understand what's in them using AI. Before it wasn't possible because of the amount of efficiency. As I mentioned before, 0.01% can kill somebody. So we need to have 100% accuracy. But what did we learn at neuromation? That currently that's impossible. We cannot get 100% accuracy. But what we can do is help doctors understand where to look, help them save time and help them save resources in order to get to the solution and to the predicted how do we call it? Predicted treatment as soon as possible. And how this is working, I mean, I'm not going to go into the details of what's happening and the exact level of how we're using different models and the scientists behind them and everything else, but as you can see, there is a linear expansion in terms of our knowledge and understanding within the medical world. And a lot of people were reaching for AI to give us the answer, but as I mentioned before, it's not possible at this given time. And we understood that, and that's what we're doing in order to create a baseline so that everybody else can understand what they're looking at and exactly where to go in terms of the treatment. So basically, to give you a little bit of an understanding of how we're doing this and what we're doing this, we're running all of these different tests on very, very, very simple solutions. It might sound like we need a whole supercomputer and very expensive hardware or software, but no. Because of neuromation's unique distributed computational network, we can use these simple specs in order to get to these results. And as you can see, this is not a huge supercomputer. This is a computer that can sit in somebody's home. And we have allowed people to access these types of computational power when other people aren't using them. So for instance, in the near future, if you have an electric car, you drive maximum 5 hours a day. The car is parked for the rest of the day. But that car has a really, really, really good computer, GPU, and a rendering processor inside it. We can access that and use that for research processes and different deep learning systems that we need to build. A little bit about neuromation and our team. We're a very distributed team from around the world. We have offices in San Francisco, Silicon Valley, Estonia, Ukraine, Russia, and Tel Aviv. We're a very distributed team in terms of our knowledge and experience. Sergey Nikolenko is our Chief Research Officer with a PhD in deep learning and mathematics, and he's heading out he's the professor of the Deep Learning Institute within the Technology University in St. Petersburg. And we've got a whole lot of over 10 different PhD data scientists within our company, with all the same mind that we want to democratize AI. We want to open up resources and allow for the small and medium enterprises to get into AI. Even the huge ones. I mean, today we've spoken to a lot of drug companies that are not utilizing AI. And why? Why is everything still manual at this time? And the reason is because it's hard, because they're lacking the data, they're lacking the resources, and they're lacking the knowledge. And that's what neuromation is here to do, to help bridge the gap between that lack. We want to try and democratize AI and allow for everyone the ability to get into this industry and utilize it for the good and for the most efficient and most profitable way possible. So before I end this story, can anybody tell me what does it take to kill somebody in terms of understanding and efficiency? I mentioned it a few times. Anyone? Come on, don't be shy, guys. You get a very nice present. Everyone will know that you're neuromation. Yes. Hey, and we have a winner, guys. The next quick question is, what is the main bottleneck in terms of AI? What is stopping us from creating these huge, amazing systems that can think for themselves? Come on, everyone's talking about it. There's a big sign behind you which says the name.
Right here, right here.
Oh, thank you very much. Yeah. Data is very important. It's very important. And, we might think that we've created a lot of data in the world, and yes, we have. But that data is only efficient to us. We need to create it in a way that computers can understand it. And that's how neuromation is bridging the gap. Thank you. Thank you very much, guys.